Hello, everyone. We are the Lighthouse Capstone group, and today we'll be briefly talking about our project, which was visible light communication via gallium nitride microLEDs. So LLMs, or large language models, have really taken over our entire lives, and everyone is using LLMs at every hour of the day. And a huge reason for why these companies are able to offer this much compute is by having a lot of data centers that can store this model and do these computations that are needed. But the issue is each data center consumes the power equivalent of about 1 million US households every year. And with the rising use of AI, this number is just poised to increase. So in 2024, a study found that estimated that we would need up to about 70 nuclear power plants by 2028 to meet our data center power requirements. And this number has only gotten higher and higher and higher every year. And a huge reason for why these data centers use so much power is because of poor interconnect technology. So existing options such as copper interconnects and co-packaged optics are pretty good for the systems that they're in, but unfortunately they use too much power and don't transmit enough data to be really worth it. Instead, we propose gallium nitride microLEDs in the process of building an array because we hope that the LED's slow and wide architecture would really compete much better than the fast and narrow communication offered by co-packaged optics. And how we're doing this is very similar to a lighthouse, where we're effectively just flashing our LED on and off with the corresponding system of pulses, and then we collect the light on a receiver and decode the particular stream of information we wanted to send. So how we plan on doing this is using gallium nitride microLEDs that we're fabricating in the UCSB nanofab and setting up a free space optical system, driver electronics, and computerized alignment to demonstrate visible light communication at scale. So first, we fabricated our microLEDs at the UCSB nanofab. Our transmit side was blue and our receive side was green, and both LEDs were around about 100 microns in size. After we fabricated our LEDs, we implemented them in an optical setup, which looks kind of like this. We have our transmit and receive side wafers being flat. That light is collected with lenses, and it's redirected using mirrors. And here's an image of our setup in our Henley lab with our receive side, transmit side, LEDs, and our microscope. And here's an image of our LEDs actually lighting up once they've been probed. To interface with all of our equipment, we have a lot of test equipment that we're using. So here's an overall block diagram for how our electronics come together. We have a function generator that drives the transmit side blue LED and an oscilloscope which captures the photocurrent that's incident on our receive side. And we have Python code that compares the two bit streams to make sure that we did our transmission correctly. Here's what our transmit side payload looks like. We first encode our bit stream using Manchester encoding, which is important because it allows us to do clock recovery. As you can see in this highlighted blue section, we have a very regular square wave for the receive side oscilloscope to really trigger onto. And on the receive side, this is the middle of our payload. We have our noisy square wave up top. We digitize that by applying a decision rule, and then we output the binary that we get after we decode it using Manchester decoding. And overall, our Lighthouse VLC system operated pretty well. We have 4 megahertz of modulation bandwidth, which is the maximum speed we can turn our LEDs on and off. Our data rate is about 1 megabit per second, and our bit error rate was 10 to the minus 4 at 1 megabit per second as well. Thank you.